All right, so today I'm going to be going over the electricity worksheet. No new content today, or even like warm-ups or wrap-ups, so you may be tempted to not even watch this. But this stuff is confusing and complicated, so I really think it's worth your time to make sure that you know how to do this stuff. Um, so yeah, because again, since school has been officially postponed until at least May 1st, so you are going to have some sort of test on this stuff that's going to be delivered, and so we're going to have to figure out um, how to deal with that and all that stuff. But basically, you do have to know how to do this. So I'm going to show you how to do this for now. Next week, we are going to start in with some new stuff, and we're going to kind of be shifting away from the field and that kind of stuff. We're going to be shifting away from that into circuitry. So we're going to kind of start that shift on Monday, and it's going to fully be into that shift going after that, leading up to spring break. So that's what you should expect going forward. But for now, let's see what we have here. So a D battery has 1.5 volts and is 6 centimeters long. Find the charge in the battery. Okay, so we have the voltage and we have a distance, and we want to find a charge. So here's our voltage equation. And so we can sort of rearrange this to solve for charge. If you multiply by R, this becomes VR equals KQ, and therefore we can switch this to be Q equals VR over K. So our Q is going to be V 1.5 times R, which is 6 centimeters, so 0.06 meters, divided by 9 times 10 to the 9. So this is going to equal 1.5 times 0.06, so 0.909 divided by 9. That's actually going to be pretty simple to get at, because it's just going to be divided by 9 billion, so that's 1, and that's 11? 8, 9, 10 zeros, yeah, it's 11. Okay, so it's 1 times 10 to the negative 11. So 1, or, well, just, it's 10 to the negative 11 coulombs. That's the charge. So how many electrons is that? Well, we have our total charge, which is 10 to the negative 11, and we know the charge of 1 electron is, well, the negative of this, but doesn't matter in this case, 1.6 times 10 to the negative 19. So you're just going to divide by that. Oops, I put the question marks in the division. Yeah, okay. So we have the charge that we got in the entire battery divided by the charge of 1 electron will tell us how many electrons that is. So divided by 1.6, and then divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There we go. So 62,500,000 electrons. Okay. What is the potential energy of 1 electron in a D battery? Okay, so we have, remember, the potential energy is charge times the voltage. So we have the charge of 1 electron, and again, in this case, it doesn't matter if it's positive or negative, so I'm just going to have it be positive, times the voltage of 1.5. So 1.6 times 1.5 is 2.4, so you get 2.4 times 10 to the negative 19 joules. And D, how fast the electron moves through a circuit? So we have this potential energy, and that is going to be equal to kinetic energy. So V squared, we're going to multiply by 2 to get rid of the 1/2. So that's going to be 2 times this, and then divide by mass. So 2 times 2.4 is going to be 4.8 times 10 to the negative 19. And then we're going to divide by the mass of 1 electron, 9.11 times 10 times 10 to the negative 31. So what is that going to equal? So we have 4.8 divided by 9.11. 0.5 527, I'll say. 0.527 times 10 to the negative 19 minus negative 31. So that is 12? Right? To the 12? Yes? I can do math. Yeah, 12. I'm actually going to keep it in incorrect scientific notation because I might have to square root it anyway. So, times to the 12, which is a trillion. That. Okay. So then square root this. Alright, so 7.26. 7 point... Wait, what is it? 7 point times 10 to the 5 meters per second, or 726,000 meters per second. Okay, there you go. There's your answers in that sense there. So this is similar to a question that you dealt with before. I think it was in the previous yesterday's homework for the voltage. Same kind of stuff dealing with that. Can you do an answer? All right. So next question here. We have the charge is that, and the battery's that long. Assume all the charge at one end of the battery. What is the field strength at the opposite end? Okay, so we want the field. And the field is solved for with kq over r squared. Now we have k, that's 9 times 10 to the 9. And we have q, we have 8.3 picocoulombs. So that's 8.3 times 10 to the negative 12. And r is going to be our distance of the battery, which is 5 centimeters. So 0.05 meters squared. So we actually have all the numbers. We don't even need the voltage. So the voltage is actually unnecessary here. So we have 9 times 8.3. You know the equals switches to the second once you press it. Okay, so that's 74.7. Again, I'm going to do wrong scientific notation at first. And this becomes 9 times 10 to the negative 12 gives you negative 3. Divided by 0.05 squared, which is, what, 0.0025? Yeah. So, we have 74.7 times 0.001, okay, divided by 0.0025. 29.88 newtons per coulomb. That's your strength of the field. What is the electric force on an electron at the far end of the battery? Okay, well, the force is this new charge times the field. And now we're saying it's the force on an electron, which means one electron. So the charge is going to be the charge of one electron. Oop, I did 91. That's a little bit less. Okay, times the field strength. And again, I'm not doing the negative. The negative in this case is just saying that the direction is the opposite of what it needs to be. But there's nothing really asking about direction here, so we don't really have to worry about it. So this is going to be then times 1.6. That's 47.808 times 10 to the negative 19 newtons, but that's wrong scientific notation, so it needs to be 4.7808 times 10 to the negative 18 newtons. Yeah, okay. That's your answer with that. Okay, 3 charges are arranged in a line, 0.1 meters between each charge. There are 2 plus 10 microcoulomb charges and 1 minus 10, the negative charges in the middle. Create the setup using electric field lab and please screenshot. Okay, so I'm going to kind of cheat and not do the exact setup just because the numbers don't line up that well for this to work. On the one hand, for one, it's 10 microcoulomb charges plus 10 microcoulomb. These are nanocoulombs, which means if I wanted to do this accurate, I would have to put 10,000 charges down. I'm not going to do that. And even if I wanted to switch this to nano, I still have to put 10 of these and then 10 of these and then 10 more of these. That's a lot. So if anything, I'm just going to be super lazy and just do 1 there, and 1 there, right? Because if you think about it here, it's plus 10, minus 10, and plus 10. The negative's in the middle. So they're all the same, right? The strength of the charge is all the same. So this is equivalent, basically. Um, the only other thing is that what was it? There was something else. It says they're zero point 0.1 meters between each of them, but how this works is that these two thick lines is a whole meter, so that means I'd have to put them all like insanely close to each other, and you wouldn't really see anything. So it's kind of pointless. I didn't realize when I because this is again I originally made this to say that draw it out because I made this from last year when you could actually easily draw this out. So that was the point there. But yeah. So when I said put it using the electric field lab, I didn't want you to be this specific because, again, that would mean you'd have to put 10,000 of these, 10,000 of these, and then 10,000 of these. They'd all have to be like, only these small lines between them. You wouldn't see anything, right? So that's pointless. It doesn't really show you anything. This at least shows you some things. You can see how the lines kind of work. Interestingly, you can see that some of the lines, like these lines, obviously go from, here's positive, negative. But see, some lines, for example, like these here, they seem to kind of bend upward, but then they kind of like go out. So you can see, for example, this line here, it kind of comes in, but then it bends upward, interestingly. So you get this kind of interesting, weird, it's like comes towards each other, but then these kind of bend out. And that's because if I just had two equal charges, right, the positive and the negative, eventually all of the positive lines are going to loop around to the negative, right? Even the ones that seem to go all the way out this way, the idea is that if you go like really far away, they'll eventually loop all the way around and come back into the negative. But you have this other positive on the other side, so it sort of has this weird thing where they sort of bend in this way, where the positive comes into the negative, but when you get up to here, the two positive lines start interfering with each other, and then they sort of bend away from each other. So it's interesting kind of pattern you can get from that. But anyway. Okay, so actual numbers. What is the strength of the electric field? 0.05 meters to the right of the negative charge. Okay, so again, the scale of this is wrong, but in other words, I want to know what is the strength of the field here. Okay, that's what I want to know to see what we can get from that answer. So we need to get the field strength from each of those three charges. So this is going to be a little tricky here. Is this there? Let's see. Yeah, okay. So we first need E1, and I'm going to say this is from... I'm just going to go in order. So this is going to be E1, this is going to be E2, this is going to be E3. So from this first one, again, we have K Q1 over R1 squared. So K is just always K. For some reason, I didn't type 9 in the first time, because I'm a smart boy. Times Q. This is your... again, it's a plus 10, so 10 microcoulombs, which I'm just going to, at this point, I'm just going to simplify to say it's 10 to the minus 5, because that's what it is. Hopefully you can see that. And now the distance, so, remember the scale of this is off by 10. So this has it being like 1 meter and then half a meter. This is really 0.1 meters and 0.05 meters. So this would be a distance of 0.15 meters squared. So what do we get? We get the top becomes 9 times 10 to the 4 divided by 0.15 squared, which is 0.0025. Wait, did I say that? 0.0225. Yeah, okay. So we have 90,000, which is 9 times the 4, divided by 0.0225. Oh, 4 million. Okay. There's like a thing in my throat. So, and we need to check the direction on this one. We didn't deal with it before for this question, but that's because we were just talking about one thing, and it doesn't really matter in this case here, but for here, since we're dealing with multiple charges creating their own fields, we have to figure out eventually how we're going to add and subtract them together. So we do need to worry about the direction. So this is the one that's coming out of this charge. So this field is going out from the positive charge. So it's going out this way. So at this position, it's going to be to the right. Okay. You know what? I'm just going to... There, just for consistency's sake. Just so it lines up nice and it makes me feel better. Okay. So now we're at K cubed 2 over R2 squared. Again. Same. Here again, the charge is the same, because remember the difference in it being negative is only going to come into play when we deal with the direction. And so now, what is our distance here? This is from this charge, so that is half a meter. So divided by, or no, 0.05 meters, sorry. So again, we end up with 9 times 10 to the 4. Now we're divided by, that's going to be 0.0025, right? I think I just did this earlier. Yeah. Okay, so we have 90,000 divided by 0.0025, 36 million. Okay, the direction this time is now to the left, right? Because it's the negative charge pulling everything into it, so it's going to be to the left. Okay. And lastly, E3 charge is again the same. That's the wrong parentheses. Divided by now, it's the same distance, right? Yeah, 0.03, same distance. Did I say 0.03? Why did I say that? 0.05. There's no 3 anywhere in here. Okay, so this is actually the same exact math as the previous one. Okay, and the direction is, well, again, all the field is coming out of the positive charge, so it's going to be to the left. So, what is the strength of the electric field? The total electric field. Let me hit backspace. The shortcut for subscript, by the way, it's control equals. So, and the equals is right next to backspace, so that's why that happens sometimes. You're going to add them up, but they have to be in the same direction. So E1 plus E2 plus E3, but again, they're all in the same direction. Now you'll notice you have 36,000 into the left, and another 36,000 to the left, and then million, 36 million to the left, 36 million to the left, and then 4 million to the right. So we'll just say left is positive, and therefore we end up with 36 million plus 36 million minus 4 million, which ends up being 68 million. Coulomb. That's not a coulomb. That's a coulomb. To the left. Okay. So, we can kind of check this from the question here. Because what does this number end up being? It says about 70. So, you can see how that started. This seemed pretty close to the 68, is what I said. Now again, 70 compared to 68 million, you might seem like, hey, that's way off. But remember, the magnitude of all of this is wrong, right? This is 1 nanocoulomb instead of 10 microcoulombs, and the distance is half a meter instead of 0.05 meters. So this will be off by a lot of factors of 10, but the number here should be pretty close. So 70, 68, yeah, it seems like that lines up pretty well. Okay, so then we're at C. A negative 10 microcoulomb charge is placed at the position in B. What is the force? What direction will it move? Okay, so here, simple enough in terms of getting the force. It's this new charge times the field. So the new charge is this minus 10 microcoulomb, so that's 10 to the negative 5. Again, the negative comes into play when you look direction. Times the field strength, which is 68 million. So 68 million times it's 10, right? Yeah. Okay. So 680. And what's the direction? Well, the field is to the left, and how negative charges work is they do the opposite of the field. So if the field is pointing to the left, that means the force on the negative thing is to the right. And again, if you think about it, that makes sense, because if you put a negative charge here, what's it going to do? It's going to want to go towards the positive charge that's closest to it, which is to the right. So, yeah. Okay. Oh boy, last question here. This is the big one. Nope, you know, there's space there. Come on. Okay. All right, so we have 3 charges in a line, plus 2 microcoulomb left, minus 2 charge. Is that the right? And minus 2 charge. Okay, so here, okay, we got to create this in the lab. So I'm going to do this a little, again, I'm not going to, let me reset it, but I want the grid and the values back. Okay, so what do I want? Let's see. 2 microcoulomb charge is on the left, and then a -4 is 0.1 meter to the right. Okay, again, I'm going to say 0.1 meter is just 1 meter just to make the scaling better. So what do we have? Okay, plus 2 micro. I'll just do plus 2 nano because I'm lazy. So I'll just do 2 of those. Try to get accurate, get it right on it, move over left one. Okay, good enough. There's your plus 2. Then a -4, which is 0.1 meter to the right. Okay, so that's going to be 1, 2, 3, 4, and then an plus 8 microcoulomb, which is to the right of the -4. Okay, so now I gotta put 8 of these. 1, 2, 3, 4. Trying to be precise here. 5. Oh, no, go right one. Okay, 6. Alright, 7, and one more. 8. I wish it did actually kind of like tell you how many there are. But anyway, okay, this kind of, I think I put it too far to the left. Oh well. It doesn't really matter. So there you go. It's gonna kind of look something like this. You have some charge. Let's see if we can kind of trace this out a little bit. So this has the smallest amount of charge, so it's mostly just going to kind of come into this -1. Now the -1 is going to sort of gather some charge in. So now there's the most of it's over here. It's the positive from the 8. So this is going to kind of curl. You can see how some of this is kind of curls right into the negative, but some of it kind of goes out before kind of curving into the negative. So it kind of like goes all the way around it. You can see how that kind of lines up that way. But some of it, for example, like here, it kind of curls up and then it just kind of keeps going up, right? So you get this kind of interesting pattern where it kind of, because basically this is the strongest one, right? This is dominating what's going on. So the negative sort of takes in the lines that it can, but it can't take in all of it because this one is too much. So even like the ones here, they're just going to kind of go out. And this one, it goes into the negative somewhat, but it's still kind of getting overpowered. Right? See how it like completely shifts around here? So it sort of gets this weird. So it's like here, it kind of moves in. It's sort of this weird kind of wiggling pattern. That's because once you get to about here, you get into this weird position where you're getting pulled in. Oh, because there's like a 0 point like right there. You're getting pulled in by the negative charge, but also the positive charge over here is like stronger, so it's kind of pushing you away. So you get this kind of weird, because you get sort of a 0 point like right about here, and you'd also get one therefore up here as well. But yes, it's kind of interesting how that comes into play. Oh, okay. What's the actual numerical question here? What is the total voltage at the +2 microcoulomb charge's position? Okay. So what is the voltage at this position? So in other words, you should take these two charges away, right? So what you want to find is what is the charge at this position from this charge and from this charge? Okay, so that's what you want. Because obviously if you think about it, well, what is the voltage from these charges at this position? Well, the distance is 0, so it's just infinity, right? That's not an interesting answer, right? So you do want to basically ignore these charges and find it from these two. So we have 2 voltages we want to worry about. We have, no, let me just, there, wait, no, okay, there. So V1 is KQ1 over R1. And so K, again, is the same one, K. Come on. Okay. Times Q. So we want it from these other 2 charges. So now we have the -4. We want to ignore the 2 because we're saying what is it at the 2 position. So we want the -4 charge instead. And again, for this one, you want to actually include the negatives because that changes your answer. Divided by the distance. Now, what is the distance? They're all 0.1 meters apart from each other. So yeah, so this is going to be at this position from this one, again, that's 0.1 meters. So the top of this becomes negative 9 times negative 4, so negative 36 times 10 to the 3, which is the same as saying 3.6 times 10 to the 4, divided by 0.1, which is therefore going to be 3.6 times 10 to the 5, so that's going to be negative 360,000 volts. Let me 100% make sure of that. So 9 million times 360 million, no, 360,000, negative 360,000 volts, okay, is the first one. The second one, we have KQ2 over R2 equals. Okay, so the other charge now is our plus 8. And now we're talking about this charge. So this, we want to know what is the distance between these two. Well, that's going to be 0.2. So we have, it's going to be 72 times 10 to the 3. For some reason I did that, no, whatever. Which is going to be 7.2 times 10 to the 4. Divided by 0.2. Which, if you may notice how this works here, this is actually also, this is going to be 360,000 volts. So, what is the total voltage? Well, negative 360,000 plus 360,000, which is 0. So yeah, 0 volts is actually your answer for B. You have 0 volts. And you can kind of check that where, of course, if I check the voltage here, you know, if I use this thing to check the voltage, you're going to think, well, wait a minute, that's clearly not 0, right? Because, you know, look how high that goes. But again, you're missing the point. The point is at this charge's position. You're ignoring this actual charge. So I'm going to just take these away. And so then, at that position, you can see it kind of zeroes out. Oop, I was almost there. Keep skipping over it because my freaking mouse is too fat. Anyway, you can see it's a 0 position right there because it goes from 0.141 to, oh, come on. It's like trying to move something that's 1 pixel in like Photoshop. Oh my god, it keeps skipping over the 1 pixel. Go. Oh, okay, there. Ha! Okay, there. See, it's very close to a 0 position. So you can see that, you know, how that works there, and you know the line for that. So yeah, that is a 0 voltage position. All right, see, what is the total electric potential energy? Well, it's the new charge, which in this case would be this charge here. We're going to put back in as that charge. So we say, okay, here we go, 2 times 10 to the negative 6. But it's times the voltage, which is 0. So the potential energy is 0. Yep. What is the total strength of the electric field at the plus 2 microcoulomb charge position? Okay, so now we care about the strength of the electric field, though. So this is going to be a bit different. Same setup, though, as the voltage one. It's just now over R squared. So, again, you might think, well, wait a minute, but like the field is like the voltage divided by a distance. So if the voltage is 0, then the field, you know, if you're dividing it by distance, then it's 0 divided by a number, it's still 0. Don't do that, okay? Because again, that only really works if you're talking about just one object. Here, since we have multiple objects interacting with each other, it doesn't really work that way. So the best thing to do is to just start from scratch here and just solve out for the electric field for each one. So again, we have, now, again, let's ignore the negative here because we're going to care about that when we deal with direction. Okay. Top is still going to be 3.6 times 10 to the 4. But now, I keep doing that. Now we're dividing by 0.1 squared, which is 0.01. So this is actually going to be 3,600,000 newtons per coulomb. And what's the direction? Let's see. So this is the field direction from this charge. Again, take off the voltage. I don't need it anymore. at this position. Okay, so the negative charge pulls things towards it, so it's going to have a negative. It's going to be pulling in, so yes, it's going to be to the right. E2 now. Nine times 10 to the 9 times 8 times 10 to the negative 6. Keep doing that. Divided now by 0.2 squared equals 7.2 times 10 to the 4, because that has not changed. The numerator is the same. But now I'm dividing by 0.2 squared, so that's 0.04. So this is not going to be 3,600,000. It's going to be 1,800,000. Double check my that 72 and that. But, yep. Okay. So now direction. Now we're talking about the field from this charge. Okay, and this charge is going out. So from this one, it's going to be to the left. It's going to be pushed. The positive charge here is pushing the field out to the left. So the total strength of the electric field, we have 3,600,000 to the right and 1,800,000 to the left. So they're in opposite directions, so we're going to subtract them. And we get 1,800,000 newtons per coulomb to the right. Field strength, 1,800,000. You can see, let's see, what does this say? Is that like 16, 18? Yep. And you can see it, yeah, that was what, 17.9? That's pretty damn close to 18. Again, the fact it's all off by many factors of 10. So the fact that this is 18, while this answer is 1.8 million, that's fine. But you can see, 18, right? It lines up, it works. So it's showing that this is working and we are getting at least something kind of decent. Okay. What is the total force on that charge? Okay, so same thing that we did with C. So the charge here is, again, 2 times 10 to the negative 6 times, but now the field, it's not 0 like the voltage, so we're going to actually have a number that's not 0 here. So what do we get? Well, let's see. Okay, times 2 microcoulombs. It's going to be that. 3.6. Oops. And the direction of this, it's a positive charge, so it's going to follow the direction of the field, so it's also going to be to the right. And, oh. How will the plus 2 charge move, assuming the other charges cannot move? Well, I mean, the initial thing to say would just be, well, it moves to the right. But let's actually think about this for a little bit. So it's going to follow the force. Oh, I already have one there. It's going to follow the force, right? So it's going to come inward. It's going to feel a force. It's going to get pushed in. And it's going to... And how forces work, right, is that it's an acceleration. So it's not like once the force, for example, changes direction here, it's not going to immediately turn around. It's going to kind of feel sort of like a... It's going to feel a sort of... what's the term? Like a... it's going to start sort of oscillating kind of between the two of them. Going to kind of get pushed back, and it's going to sort of oscillate like this. Because once it gets in, it's going to sort of... It's just how, like, if you're driving a car, but you but you slow down with the brakes, you don't immediately stop and turn around, right? You slow down, and then you kind of... And then you kind of keep going, but the force is still pulling you backwards. So you'll... And not only here, you will... Because look at the voltage here, right? So here, the field strength. So here, it's like 120. Here, it's like, 420. So... There's going to be a lot, because when you're here, you're getting pushed by this charge to the left, and you're being pulled by this charge to the left. Whereas over here, you're being pulled by this charge to the right, but you're being pushed by this charge to the left. So it's much stronger over here. So it'll be kind of like a thing where it kind of slings it out, and then it will kind of fall out, and then it will come back in and sling out, and then kind of go out like that. It'll be sort of this weird kind of oscillating pattern like this. But it's going to be not symmetrical because of these positive charges here. I'm not sure how far. I guess you'd have to figure out the exact numbers in terms of the acceleration and like use actual kinematics to figure out how far out it goes, because you could get in a situation where it gets slingshotted out by this one so much that it gets pushed out to here, and then all of a sudden the field starts now pointing. I don't know if you can see this, but it's in the other direction. You can't really see that, but because here's like this about the 0 point, and you can see this is 0 point like right about here-ish. So that means over here it's pointing to the right, but once you pass the 0 point, see now the number's increasing, it's now starting to point to the left. You can see these arrows here. See how these arrows are pointing to the left? They're really faint. So once you actually, if it does actually slingshot it out past here, then it actually will just keep going to the left. So, yeah. So it depends on how you want to describe it, how specific you want to go. If you want to just say initial movement is to the left, and then it will likely oscillate asymmetrically. I don't know if you want to. That's not useful asymmetrically. There's no S in asymmetrical. There's two M's though. Yeah, asymmetrically. Okay. Around the negative charge, unless the positive charge is strong enough to push it out past the 0 point of the electric field, and then it will just keep going left forever. That's too much information, honestly. You don't need to... Oh, initial moves not to the left, it's to the right. Okay. Initial moves to the right. So, yeah, that's too much information. But basically, you sort of see what I'm talking about, where probably it's going to kind of come into the right, and then it will sort of oscillate this way, get pushed out by that one, and then sort of kind of probably follow some sort of pattern like this. But if it's strong enough, it will push it out forever. So, and that just depends on the exact calculations of the force and the, we don't have that information. You would actually need to know the mass of this charge anyway. So, yeah. But it's something to think about at least. So there's that, I guess. I don't know. You can see how this can get kind of complicated to figure out a lot of the specifics here. But there you go. That's that. That's kind of what what you can see you can come at. So, hopefully you kind of could figure out most of this stuff. Again, we're going to be switching gears a bit to something a bit different. Before the end of the unit, we will sort of come back and review this again. But for now, this is where we're at with this kind of stuff. So if you were stuck on these things, hopefully these explanations can help you. Again, I think that this content on this worksheet is probably generally the hardest stuff for most people, like in the entire year. So keep that in mind, I guess, in terms of while you're going through this and seeing how you do. But yeah, so there you go. Monday, there will be another Kahoot on Twitch. I know there was sort of a delay, so I'm gonna be I'll have the timers extended. The thing is, I'll have it probably be like an hour, not an hour, a minute, an hour long Kahoot. Good lord. There'll be a minute for each question instead of 30 seconds. So that should help with the delay. Yeah, and then we'll start, and then there'll be a video on Monday going into, well, we're starting with sort of the transition into circuits. You'll see how that works there. Yeah, the circuit stuff, you don't deal with nearly as much gross numbers. The numbers are usually much nicer. But the rules for circuits are pretty simple on the base level, but it's one of those things where the rules build off of each other and you get much more complicated examples. I kind of like it in sort of how complicated it can get, because it's sort of like, I think of it as like a puzzle. So you'll see. I think most people like it more than this stuff, at least. But yeah, so we'll see how that goes. Yeah, so that's what you should expect going in for Monday. So for now, that's that.